Happy Wednesday, you guys. Hope you guys are doing really well. Um, Again, we're in chapter 7 here where we're talking about integration techniques. Now, just as a review of schedule, tomorrow, Thursday, is a quiz, quiz 12. That quiz, just so kind of allay some fears here, the quiz is going to cover hyperbolic trig functions. So that's just derivatives and integrals, kind of like what was on the homework. Shouldn't be too crazy. I can ask you for definition of hyperbolic sine, definition of hyperbolic cosine. So you should remember those. Um, but otherwise, the derivative of sinh is cosh, and the derivative of cosh is sinh. And otherwise, you're doing integrals according to using those techniques. So now, chapter 7, and then the rest of the quiz can cover just general integrals using our integration techniques up through integration by parts, and then a very simple integration by parts that like what we covered on Monday. So basic integration by parts, maybe you might need to do it twice. Okay, so the integration techniques, again, just as a review that we covered, are number 1, if you can't do the integral immediately, you try to simplify. That might mean multiply out. That might mean divide out. That might mean do long division. If you've got a polynomial over a polynomial and the top degree is bigger than or equal to the degree of the bottom. Otherwise, we had the technique of substitution. And again, the thing that we look for substitution is we're looking for composition or the du or u. And here we let u equal that inner function if we see a composition, right? Okay. Or if we see that one thing in the integral is the derivative of something else, and we let that something else be u and this thing be the du. So last time we talked about a new technique called integration by parts. So I abbreviated that IBP. So again, this is 7.2, integration by parts. And for integration by parts, the idea is we had an integral that was a product of two things. Okay, so we're generally looking for products here. So it's not actually going to be listed as u times v. So we might have a function, the product of two functions here. And what we do is we let one of them be u, and then the rest of this be dv. Okay, and this was motivated by reversing the product rule. So integration by parts is a reversal of the product rule. And then what we would do is we would figure out what du would be, and we would figure out what v would be. And we use the formula, the integral of u dv equals u times v minus the integral of v du. Okay, this is our integration by parts special formula. I'm actually going to write it up here because we're going to use it several times today. Okay, that's our integration by parts formula there. All right, and the idea is hopefully we picked these in such a way that this integral was hard, but this integral that we end up with later is easier. So we're looking for products, and we let u equal part of that and dv equal the other part of it, and we compute du and v and then use this formula, okay? Yeah, so we've looked at several examples here. One of the notes that I made that I'm going to go ahead and make here is that you may need to do integration by parts multiple times. Okay, may need to do integration by parts multiple times. Okay, that was motivated by, we saw an example like x squared e to the x. And when we did integration by parts, we ended up with an integral x e to the x, which means we would end up wanting to do integration by parts again. Okay? All right. Now, there's a couple of other things that can come up with integration by parts. Let's see if they're, let me just check real quick here and make sure. For any of the homework problems. Now, one thing to notice about the homework, let me point out a couple things here. So this is section 7.2 homework. So for instance, if we take a look at number 9, they don't actually tell you to do integration by parts, but they ask you to pick what would you let be u and what would you let be dv. You know, I don't even think they make you explain why. Now here, for number 9, I would actually let u be x and dv be secant squared. The reason is that thinking through that choice, du would be dx. This is all that you actually need to write. But thinking through that choice, du would be dx. V would actually be tangent. And notice that this would actually equal u times v, x times tangent, minus the integral of v tangent du. Comparing these integrals, the integral of tangent is actually much easier to deal with than the integral of x secant squared x. There's no x down here, right? There's an x up here. Tangent is actually one of the ones that you're supposed to have memorized. Okay, secant is one that we're supposed to have memorized, and tangent is one that we're supposed to have memorized. And if you've forgotten, the integral of tangent, I'll just write it over here, is negative natural log of absolute value of cosine x. Okay, that was one of the ones I told you, hey, memorize this, it's going to come up. Another one that I told you to memorize is secant. Oops, I didn't put the dx there. And the antiderivative of secant is the natural log of the absolute value of secant plus tangent. Okay, memorize those if you have not memorized them. Okay, they will come up. So you didn't have to write, on this problem, you didn't have to write anything beyond that, but this is the motivation why we want to let dv be the secant squared and u be the x. Okay? So that's taking a look at number 9. The warning that I have is that on some of these problems, particularly number 14 and number 18, you want to use substitution and not integration by parts. So even though there's a product in there, you generally, in this list of techniques here, there are certain techniques that are easier, and you're looking for those techniques first. Integration by parts, in general, integration by parts is going to be one of the hardest techniques that we have. So you generally don't want to go, oh, product, do integration by parts. You want to try to do something else first, and if integration by parts is your last resort, or you recognize, yeah, I have to do integration by parts on that, then do it. But in general, like on number 14, you would let u equal 1 over t, because 1 over t squared is kind of like the du. And on number 18, you would let u equal natural log of x, because you see that du of 1 over x that's there, okay? So number 14, number 18, you're not supposed to be using integration by parts there. All right? Okay. Just to do maybe one more, let's take a look at number 11 on the homework, just so I can check to make sure that you're following, and I want to say something about this. Okay. Here, on number 11, what I would do is I would let u equal x and dv be e to the negative 2x dx. The reason is that I would love to see that x go away, and if I let u equal x, then the du is going to be the dx, and that x won't really be there anymore in the integral. The reason I bring this example up is I want, what is the antiderivative of e to the negative 2x? I think you can do this, you can start to do this in your head because this is going to come up a lot. Okay? If I differentiate e to the negative 2x, I get negative 2e to the negative 2x, right? Remember that? We talked about that repeatedly. So that means if I want to go backwards, I'm going to get a negative 1/2 here. Okay, so when you're anti-differentiating, which is what we're doing here, we're going to get a negative 1/2 e to the negative 2x. So that means here that this integral works out to be u times v, so negative 1/2 x e to the minus 2x, minus the integral of v du. So in other words, negative 1/2 x e to the minus 2x plus 1/2 integral of e to the minus 2x. And I want you to start being able to do that e to the minus 2x in your head. Okay, you should be able to say that's just negative 1/2 e to the minus 2x. Okay, and I can multiply those two together to get negative 1/4. But that is my answer that comes from integration by parts. Okay? So there's a few more things I want to say about integration by parts. There's actually 3 other things I want to say about it, and then you should have some more time if you need some more time to work on the homework and or ask further questions. You'll have time to do that, okay? All right. Let me leave that up here just for a second. Okay, so what are some other ways that this can get complicated? So we're looking for products. We remember that we may need to do integration by parts multiple times. There are a couple of other things that we have to keep in mind. Okay, another thing that I want to point out is that sometimes the product that you're looking for is 1 times another function. Okay, let me explain what I mean by that. So let me give you an example here. Let's do the integral of natural log of x dx. Okay, this, truth be told, this does not look like a product. Okay, and when I first encountered this, now I've done this enough that I would know I need to do integration by parts on this. But if I just encountered this and I'd never seen it before, I'd sort of figure out, is there a way to simplify that? No, there isn't anything really to work with there, so I can't really like multiply out or divide out or do other things like that. Is there a substitution? Well, I don't see a 1 over x here, so I can't really let u equal natural log. That doesn't help me. So what can I do here? Well, I'm kind of stuck having to do integration by parts. So the thing is, if you go through these other 2 techniques and there's really nothing to do, and you're stuck, you kind of, by process of elimination, I know I have to do integration by parts, but it's not really a product, but if you think of it, if I let this be the u, then the only thing that I can do is let the dx be the dv, right? So let's just follow this now. So du would be 1 over x dx, and v is going to be x there. So in keeping with my formula, I'm going to have u times v, so x times natural log x, minus the integral of v du. Now watch what happens though. That x times 1 over x just becomes 1, so I just have the integral of dx, and that's a super easy integral. I'm done. Right, so what's weird about this problem is it doesn't look like a product, but if I think of it as kind of like 1 times natural log, then that's where that dv is actually coming from. So sometimes it doesn't look like a product, but it actually is a product. And one of the motivations is that working with natural log is hard, but working with its derivative is much easier. So I end up using integration by parts because I want to work with the derivative there. That make sense? Let's try another example here. Let's do the integral of arcsine. Again, I don't see a product there, but there really isn't a way to simplify that. And there's no immediate substitution. I don't see a composition, and I definitely don't see the derivative of arcsine in there anywhere. Like if I saw this over the square root of 1 minus x squared, then I might do a substitution, but there's none of that's in there. So I'm stuck having to do integration by parts, and so I'm going to let u equal that thing, because I would much rather work with it than with its derivative than with the original function itself. And so dv has to be this dx. So then du is going to be the derivative of arcsine, which looks like this, dx. And v is going to be x. And so then I'm going to, using my formula, I've got u times v, so x arcsine x, minus the integral of v times du, which is this. Okay? Now comparing integrals, you look at this and you look at this, you might think, well, that's a little more complicated. But in fact, arcsine, I have no idea what to do with that. This is something that we've seen before that we can actually do something with. How would I do that integral? How do I do that integral? Yes. Notice that I have an x dx here. That's kind of a signal. That's the kind of the derivative of what's inside here. So, and I see a composition. So here, I'm actually tempted to do substitution. U equals 1 minus x squared, and so du is going to be negative 2x dx. And lo and behold, that x dx is sitting there. So let's keep going. We've got 1 over the square root of u, and then we've got a negative 1/2 du. So cleaning that up a little bit, I've got a plus 1/2 integral of u to the minus 1/2. That is an integral I can do, and that's the point. We're trying to get, it doesn't get rid of the integral, but it makes the integral simpler. So now I add 1 to the power, so u to the 1/2, and then divide by that, which is the same as multiplying by 2. And now I just have to substitute back in. Okay, the 1/2 and the 2 cancel. So I get square root of u, and u is 1 minus x squared. Done. Okay, so even though I don't see a product here, it is kind of a product. It's going to be 1 times the function, or the function times dx. Okay? So that's something to watch out for. You may see a product, but you may not see a product, but there actually is a product there. Okay? So that's another thing to keep in mind. You may need to do integration by parts multiple times, and you may be working with a product that's just 1 times the function. Okay, another thing that I need to mention is how do we do this with definite integrals? Okay, here's what I mean by that. So let's go back to a problem that we did originally. The integral from 0 to 1. The integral of x squared of x e to the x dx. But now we're, instead of being just a general integral, we're going to do it from 0 to 1 this time. All right. So let's, ignoring the 0 to 1 for a second, the way that we did this before is we let u be x, and then this part right here is my dv, so e dx dx. So du is dx and v is e to the x. Right, we did that because working with the antiderivative of e to the x is fine, but differentiating x makes it nicer. So my answer, if there were no 0 and 1 here, would be u times v minus the integral of v du. Okay, that would be if there was no 0 and 1 there. How do you think this changes if there is a 0 and 1 there? Well, what do you think I do here? I think probably clearly I put a 0 and a 1 here. What do I do with this thing? This is a number, so I should not leave this the way that it is because my answer would end up being x e to the x, which is not a number, it's a function. So as you would probably suspect, I need to evaluate this like it's an antiderivative from the two limits of integration, so from 0 to 1. So what that means is I need to plug in 1 times e to the 1, minus plug in 0 times e to the 0. That's how I take care of this part right here. Don't leave that as just x e to the x. If you have a definite integral, this should be a number that results from here, so you should get numbers out of here. If you get functions at the end, you did something wrong. Okay, and then I'm going to go minus antiderivative of e to the x is e to the x from 0 to 1. So I've got e minus, this is just 0, minus e to the 1 minus e to the 0. And I just plug in both. So I've got e minus e plus e to the 0 is 1. These cancel, so the area there is just 1. Okay, so working with definite integrals is not that much more complicated in the integration by parts than working with just without definite integral. The only thing that you have to remember is please, please, please don't, at u times v term, please plug in. Don't leave it sitting there. All right. So that's another thing to remember. Okay. The last thing is kind of a weird thing that shows up with integration by parts. Okay. This is a weird situation that only shows up with integration by parts. And I call this, I give this a weird name. I think somebody else gave it this name. I don't really like this name, but that's what I've always heard it called, and I don't have a better name, so I call this circular reasoning. Okay. Now, what in the world do I mean by circular reasoning? The best way for me to describe this is to do a problem and show you something that's happening here. Okay. So let's take the example e to the x times sine of x. Okay. And I'll show you two examples of this sort of circular reasoning. So I'm just gonna pick e to the x. It turns out it doesn't matter which one you pick to be the u and which one you pick to be the v. So I'm gonna pick, I like anti-differentiating e to the x. It's really easy. The antiderivative is just e to the x. So I'm going to let u equal sine and dv equal e to the x dx. Okay? So du is going to be cosine and v is going to be e to the x. Everybody clear? So I see a product, I'm going to try integration by parts. There's nothing else I can do with this. So the answer, this should be u times v, so e to the x sine x, minus the integral of v du. Okay. Everybody follow? So e to the x sine x, u times v, minus, oh, and I didn't write dx here. V. Okay, now comparing integrals, notice that this one isn't worse than the first one, but it's also not better. It's actually basically the same difficulty level, which is kind of interesting. So keeping that in mind, we might persevere and say, well, maybe I just need to do integration by parts again. So let's try that. So I'm going to let cosine, so the same, since I let sine be u, I'm going to do the same thing. I'm going to let cosine be u. And dv be e to the x dx. If you switch these, and you let u equal e to the x, you're actually just going to undo all of the work, and you're going to get back to the original thing you had. So my du, the derivative of cosine is negative sine, and my v is e to the x. Okay? Follow? So I'm just trying this multiple times to see what happens. Okay. So I've got e to the x sine x minus, so I'm going to use parentheses here, I'm going to be careful. So I've got u times v, e to the x cosine x, minus the integral of v times du. Okay, and I have to be super careful about my negative signs here. So let's clean this up a little bit. I've got negative e to the x cosine x. Minus is minus integral of e to the x sine x dx. Okay. Now I want you to step back and notice something here. I started with e to the x sine x, did some work, and I ended up with the integral e to the x sine x, which seems like maybe I wasted my time, but actually you didn't, and here's why. So if I call this integral, I want you to just think about this for a second. If I call this integral I, then what's going on here is I have I equals some stuff minus I. So if I were to bring this I to the other side, I get 2I equals this stuff. So I can actually solve for the integral. The I would be 1/2 of that stuff, right? So this technique is what we call circular reasoning. You start with an integral, you do integration by parts a couple of times, and then you end up with the same integral back again. But it turns out that you can, thinking about the integral equals some stuff minus some multiple of the integral, if you can pull that integral to the other side, then you can actually solve for the integral. So in this specific case, if I pull this integral to the other side, I get 2 of them. So 2 integral of e to the x sine x is going to be this thing. E to the x sine x minus e to the x cosine x. So if I divide by 2, I end up getting that e to the x sine x is 1/2 of this stuff. And of course, I still need a plus c because this is a general antiderivative. Isn't that cool? I don't know. The first time I saw that, I thought it was like weird, kind of magical. I don't know. It's just weird. Okay. That makes sense though. So I did integration by parts twice. I got this other integral, which is the same as the integral I started with, so I pulled it to the other side. I got 2 of them, and then just divide by 2, and I was able to actually solve for the integral. It's kind of cool. All right. Okay, let me do one more example of this, and then I'll let you guys go ahead and work on the things that you need to work on. Let's do another example of this. So typically, let me just say, if you ever see e to the x times a trig function like sine or cosine, usually that's an indication that circular reasoning is going to come into play, because differentiating sine twice is going to eventually get you back to sine, whereas integrating e to the x is going to keep you at e to the x. So these types of things, or e to the 4x cosine x, these types of integrals you're gonna do with this circular reasoning technique. Okay? And I think there's 1, maybe 2 examples of that on the homework. There's another one that shows up later in the next section that we're going to get to, and I'm going to go ahead and do it now because it's a nice example of a integration by parts. And it's secant cubed. Now, for secant cubed, there is not really a way to, one way that I might think about simplifying this. So if I were to think through if you gave me this example, secant cubed, the first thing that I would think about is, okay, is there a way for me to simplify? Well, secant is 1 over cosine, so maybe one way that I could simplify would be to make that 1 over cosine cubed, which might make me think of doing a substitution, but I don't see a sine that's the derivative of cosine. I don't see that anywhere. So that's probably not going to work. Another thing that I might think about doing, so that's out. Another thing that I might think about doing is, if I'm looking for a du, notice that secant squared is something that I can integrate. Secant squared is the derivative of tangent. So if this was tangent, and this was secant squared, then I would let u equal tangent, and the du would be secant squared. But this isn't tangent, so that's not going to work either. Okay, that's kind of out. So none of this really seems to be working here. So I'm stuck doing integration by parts. Okay? And in order to do integration by parts, one portion of this I have to differentiate, and the other portion I need to integrate. Now, I can't integrate secant cubed. That's part of my problem here. I can integrate secant, but it's a mess. So I'm not going to integrate that. So I'm kind of stuck having to integrate secant squared. So that means my dv has to be secant squared, which means my u is the other part. So du is going to be the derivative of secant, which is secant tangent, and v is going to be tangent. Okay. So following my nose here with integration by parts, I'm going to say this is u times v, so secant times tangent, minus the integral of v du. So I've got secant, and then I've got 2 tangents, so I've got tangent squared here. Okay, so secant cubed, the integral of secant cubed is secant x tangent x minus the integral of secant times tangent squared. Okay. Now, that's all well and good, but I can't this, I don't really know how to do that any better than I know how to do this. But here's a little trick that we're going to see more of in the next section. We're not going to do this trick right now a lot, but you're going to see more of this trick in the next section. There's actually an equation, an identity that we have between tangent and secant. 1 plus tangent squared is secant squared. Do you remember this identity? Came from sine squared plus cosine squared equals 1. So 1 plus tangent squared is secant squared. So tangent squared is actually secant squared minus 1. So what I'm going to do is I'm just going to sub in for that tangent squared, I'm going to put in secant squared minus 1. Now here's how that helps me. I have secant times secant squared, so that's the integral of secant cubed. Then I've got a minus is a plus. 1 times secant is just secant. Okay. Now notice that we started with secant cubed, and now we ended up with secant cubed. This right here, secant, is an integral that I can do, right? Secant is one of the ones that I told you to memorize. So again, I've got this integral, I equals some stuff, which I know how to do, minus I. So if I add this I over, I get 2 of these integrals, 2I. So in other words, 2 secant cubed is this thing plus this integral, which we know how to do. That's natural log of absolute value of secant plus tangent. So in other words, the integral now we can solve for. It's 1/2 of this thing plus 1/2 of this thing plus C. Is that cool? I don't know, it's just weird that you do it a couple times, you get back to the thing you started with, and that turns out to allow you to solve for it. So I call that circular reasoning. It's not really circular reasoning, but you start with your circular reasoning is kind of, the term circular reasoning, for those who haven't encountered that term before, it's a fallacious logical argument. So if I were to say, why are you angry with me? And you said, because you stole my book. Because I, I'm angry with, sorry, if I were to say, if you were to ask me, why are you angry with me? And I said, I'm angry with you because I don't like the way that you look. And you said, okay, well, why don't you look like the way that I look? And I were to say, well, because I'm angry with you and I don't like you. That's actually circular reasoning, because if I say that I hold this stance because of this and I hold this stance because of this, there's no actual solid ground or justification behind why some of this works. So as an example, I've mentioned something about radiometric dating. One of the things that's classic in radiometric dating to date rocks is that we say this rock is a certain number of years old because we find these kinds of fossils in it. But then people make the argument that these fossils are a certain number of years old because they're in these rocks. And that ends up being a circular reasoning, because you're basing the age of this on the estimated age of this, but you're basing the estimated age of this on this. So who knows what the actual age is? That justification does not give you any sort of solid ground to justify the actual age of something. Okay, But so it's circular reasoning in that you start here and you end up back here again. That's why we call this circular reasoning. But this is a sound logical argument. Circular reasoning is not a sound logical argument. So hopefully that makes sense. All right, so don't forget, you've got a quiz tomorrow. Again, the quiz covers hyperbolic trig functions, and it covers the basic integration techniques, simplifying and substitution, and basic integration by parts. So identifying things as products that you may need to do integration by parts multiple times. I'm not going to give you the things that we went over today. That will be on homework that's due next Monday. Okay? So have a great rest of your day, and I will see you tomorrow.